Maybe I should ring the bell again. Right. So, yes. Okay, let's resume. So, our next talk is going to be given by Nicolas Mordant from Université Grenoble Alpes, and it's going to be on experimental investigation of soliton gas in shallow water experiments in 1D and 2D.
Okay, thank you very much. Thank you for the introduction. And thank you for inviting me this prestigious place. Actually, it's a great pleasure to be here. So I'm doing experiments, as you can see here, and so most of the results I will show come from the PhD of Yvan Redor and the ongoing PhD of Thibault, who is in the room somewhere, with my colleagues Eric Barthélémy and Hervé Michalet in Grenoble, and from results also from many discussions with Miguel Honorato, Eric Falcon, and his PhD students. Okay, so actually, I won't have a single equation, I think here, only experimental results. It will be a hard week for me, actually. Okay, so just beyond the motivation of the beautiful theory of integral turbulence, I think I want to mention also that my motivation also comes from the fact that you can observe this in real seas, actually. So that in this paper in 2014, there is this record in the Connecticut Sound of North Carolina, which is a shallow water kind of laguna. Depth 2.6 meter, and for I don't know the size, the horizontal size, but it's very large. And you see this record, and when they filter out the fast oscillation, now you can see the shallow water solitons that emerge. And when you look at the frequency spectrum of this data, there are several ranges of frequencies that have been highlighted by the authors. So the low frequency is associated to soliton turbulence. Then there is a band where they claim that it's modulational instabilities, Benjamin Fair instabilities here, and then followed at high frequency by weak wave turbulence. So we see that in this single record, there are many features that are quite different, actually, from what we have heard also just before on Stéphane's talk. So now the question is, what can we do in the lab? So Stéphane did a very nice introduction of my work, actually. I was a little bit scared that I didn't have any remaining slides to show, but okay, so we are in the Grenoble, we have a 34-meter long flume like this, where we have a big piston wave maker to excite the wave, and we have a vertical wall at the other end, so that is reflective, and we get bidirectional propagation. So that to keep the soliton as long time as possible in the flume, actually. So we have glass windows on the side, so we actually measure the wave elevation by just putting 8 video cameras on the side, each one measuring the water elevation on one of these windows, so that at the end we have a time resolved measurement over 16 meters, so like half the wave flume here. So if you really want a equation, so it's 1D shallow water wave, so it's KdV, except here it's bidirectional, so it's rather Cobb-Boussinesq, which is a bidirectional version of this. Okay, so the first thing I want to emphasize here is that real life is not really integrable. There is dissipation in experiments. And you can see that here, it's a plot of the amplitude of a single soliton going back and forth in the flume as a function of time. And you see that it's clear, the amplitude is clearly decaying over a relatively long time. It's almost 10 minutes here, but it starts at 7 centimeters down to millimeter scale. And this is just viscosity on the walls, actually, on the bottom and the side walls, as was actually calculated by Culligan in the 40s. But still, if you look at 2 different times, the amplitude of the soliton decays, but it remains a soliton. So it's some kind of adiabatic decay. So at short time, we can still assume that it's a soliton. Now,
when you have a reflection, like right after the reflection?
Well, there is most likely a little bit of dissipation, but it's mostly during the propagation of the 30 meter that you lose most of the energy. The impact is almost negligible here. And as I come from weak turbulence, actually, rather than integrable turbulence, I like stationary state. So if you have damping, if you want a stationary state, you have to force. So we keep forcing, putting soliton in the system. And the consequence of this is that the amplitude of the soliton will be distributed. All solitons will be small, and young solitons will be large. Okay. So now, but despite that we have this dissipation, we still keep the building bricks of integrability that are these two soliton collisions. So the overtaking collision and the head-on soliton. So here we see from the 7 video cameras, so there is a big soliton chasing a small one. And in this field, you will see that they are almost equal in amplitude. And then there they have exchanged, the big one is in front of the small one, which is what you expect from KDV here. And because it's bidirectional, you also have the head-on collisions that occur as well. And they are characterized by this big peak at when they are overlapping, actually, which is higher than twice the amplitude of the soliton. Okay, so now we have this 3D, 1D space and time resolved measurement. So you have a 3D rendering here, where you see the time here, the position, x position there, and the amplitude in color. And you have all these red peaks that occur here that are head-on collisions. So we see that we succeeded to have something that begins to look like a soliton gas, with lots of solitons everywhere. And how do we do that? That's what Stefan told you before. We can't generate many solitons one by one by the piston, because to do that, the piston has to recede very slowly and then push forward very fast to generate the bump of water. And the receding phase takes almost the time it takes for the soliton to do a round trip in the flume. So what we do is we use the Bouski and Crystal observation that when you force a sine, it makes a fissions into a train of soliton that become random because of this forcing and dissipation, actually. So at the end, we have a random state like that. And because we have space and time, you can do Fourier transform in both space and time, and you get this kind of picture where you have different lines that can be highlighted. The first one is the straight line, which is square root omega equals square root of GHK, which is associated to the solitons, actually, and the dispersive waves that we branch, that is curved here, that we see a little bit. So we have a little bit of energy in both branches, but the fact that we have this straight line is clearly the indication that we have solitons in there. If we just look at the frequency spectra as in the data I showed you before, we have a spectrum which is like this. So we have 3 curves that correspond to the full signal in blue and the wave going to the right. If you take only this quadrant here in the Fourier space, you have the wave going to the right, and in a yellowish color, you have the wave going to the left. All curves are very similar except from the damping. And the typical spectrum of our soliton gas is a flat region at low frequency followed by exponential decay that Stefan told us it's typical of soliton gas. But we can also do the direct transform, scattering transform of this signal. So what we do is at one position, we take like 60 seconds, like here, record of the elevation, and we do the ST of this record, and we get a number of solitons. Here you see that in this 60-second record, we have like 50 solitons at that position. And with this this collection of amplitudes, actually, we can compute a distribution of soliton amplitude. So it begins to look like a density of states, actually. And you can do that at different positions along the propagation of the soliton. So that's 10 meters after the wave maker, 20 meters, 40 meters, and 60 meters. So wave coming back, actually, after the reflection. So the boxes are the distribution of the soliton, which is a little bit strange with 2 bumps. And this comes from the fact that we have to force continuously, actually. And when we go from the first box to the second one, actually the red curve comes from if we take the damping law of the soliton over 10 meters, then we get the dashed line from this one, and you see that the agreement is fair with what we measure there, and it remains fair but not so good at much longer propagation distances, but still mostly the evolution of the distribution comes from the damping actually. And of course, if we would do that back to the first position, we would get the green thing, but we have much stronger solitons because of forcing. And with the forcing, we observe that actually there are two effects of the forcing. One is the fact that you generate new solitons that are relatively large, but also it can amplify all solitons if they came with the right phase with the piston motion. So we can have huge solitons actually that come out of this. Okay, and then at the end, we get to some kind of phase diagram. In principle, the KdV equation has only one dimensionless parameter, but what we see in the experiment is that we need a second dimensionless parameter that we take here as the nonlinearity, the other one being the Ursel number, so the ratio of the nonlinearity over dispersion. In principle, we would just, in ideal world, we would just need the Ursel number, but in reality, we see that we need a sufficiently large level of nonlinearity to observe soliton gas in blue, whereas for the red dots is mostly sine remains a sine. Okay, so it doesn't evolve into a soliton gas. And actually, there's also another limit, which is the transition from deep to shallow water. If we put two small wavelengths, then we are in the deep regime here. But nothing really happens in that case. Okay, so after looking at this, we said, okay, well, maybe it could be fun to actually go to 2D. And in Grenoble, we have this, we have a nice facility, which is owned by the Artelia Group, actually. So it's a private company. So it's a 30 by 27 meter square tank, with one side being made of 16 independent piston wave makers, so that you can generate waves with a very complex shape, in particular wave with an angle to the wall. Okay, and and the depth is 37 centimeter here, so we can go there with boots in the experiment. So now in terms of measurement, so we still have the classical single point local wave gauge that measure the elevation and function of time. So we have like 25 or 28 of them scattered around in the tank. But we really wanted to have this, again, this time resolved measurement. So what we did is that we put like 300 kilograms of plastic particles in the tank floating at the surface, so that to mark the surface of water. And we have two cameras that are just outside the field of view of this movie, so in the corners here, looking at the surface, so that you have a stereoscopic view of the surface, so that you see in the two displays at the bottom the image seen from each camera, and when there is a soliton going there, you see the motion seen from your two eyes somehow. Okay, and from this we can measure the wave elevation over an area which is about 10 by 10 meter out of this 30 by 30 square. So it's a decent area of the tank, and we have single probes around here, so that to do a comparison with the 3D reconstruction. Okay, so the first experiment to show is just a single soliton. So in terms of integrable equation, is the Kadomtsev-Petiashvili equation that's supposed to describe this in an infinite world. So the solitons are line solitons. Okay, so what we want to do here is generate a soliton with an angle to the wave maker, so that at the end to be able to send solitons with different angles. So the wave maker will start at the back here and then propagate to the front. So you will generate a soliton there that you begin to see a little bit, and that appears here in the 3D reconstruction that Thibaut did. And you begin to see the difficulties of real life is, well, first, obviously, the solitons are bouncing on the walls because the space is not infinite, and also we get a very complex shape of on the reflection, and after the reflection with a curved soliton somehow. Well, curved crests. It looks like soliton, but it's not so clear whether they are actually soliton. So let me show you just two snapshots of this thing. So that's the first snapshot just after the emission of the soliton in the field of view of the camera. So the first thing you see is that the soliton is bent, actually. It's not a straight line, and the amplitude is decaying in this bent region. And that's very similar to what was shown in this paper by Riskamp, Maiden, Biondini, and Mark, where they generated a truncated soliton in the Kadonsev-Petit-HVD equation, and they see also this kind of nonlinear diffraction of the soliton and the fact that it's bent and the amplitude is decaying along the soliton. So it's very similar to this kind of thing. And in our case, it comes from the fact that the wave maker, they have a finite extension. And then there are the reflections at the walls. So it's well known for a very long time, actually, that linear soliton hitting the walls generate a peculiar feature here that we see from this paper, this review by Kodama, another experiment, actually. So this kind of Y-shape, the wall is at the top here. So a Y-shape structure with a large amplitude on the wall here. In our case, the wall is at the bottom, and we have very similar things. So at the end, we have all this together. So that after reflection, we have crest moving all the way that are bent and this structure on the walls. So now if we want to go to some kind of soliton gas, we can try to generate. So in that case, we generate soliton one by one. So it's an extremely diluted gas, more rarefied than even diluted, but still. So you see from many crests, and from time to time, a big one that comes that was just generated by the wave maker with some distribution of angle between plus and minus 30 degrees. And that's the water elevation distribution in that region here. So the two curves are either the stereo reconstruction from this movie in blue, and the red one are the probes that are just at the periphery. So we see the agreement is very nice, actually. And what we see very clearly, this very strongly skewed distribution of the PDF that Stefan showed also, that is also typical of the presence of solitons, actually. And because we have to conserve water, if we put water in the soliton, it means that the reference level of the water will become negative, actually. And that's what we see here. The maximum probability is clearly negative by a couple centimeters. Now we can also compute the frequency spectrum of the water elevation here. So again, the two curves correspond to the two measurements. And we see again this very nice exponentially decaying spectrum. It is also typical of at least the diluted soliton gas that we saw in 1D as well. So a flat region here followed by an exponential decay. And if you go to now the K omega spectrum is a 3D object, so Kx, Ky, and omega. So I have to do cuts to show you this spectrum. So that's a cut for Ky equals 0. So in the X direction, which is the one orthogonal to the wave maker, so the one on which we emit the soliton directly, so frequency versus Kx. So we again see the line of the soliton dispersion relation, and then the dispersive waves. And we see that actually the energy on the soliton branch is actually inside this cone of these two straight lines. That means that the solitons are actually getting faster than square root of the h, as they should, actually. I mean, there is this correction in amplitude. And now if you look at the y direction, there are no solitons at all. Even though the reflections that we saw are sending something that look like soliton, the localized waves, actually, they are not soliton, they are just dispersive waves, and they are very faint, actually. There is not so much energy in these two branches. And if you look at cuts at a given frequency, so in this 3D matrix, we choose a frequency here, and we have Kx and Ky there for 4 different frequencies. These dispersion relations are circles now. So the inner circle is the non-dispersive one, the linear dispersion, and the outer circle is correspond to the dispersive wave. And we see that most of the energy is localized slightly inside the inner circle, but also mostly localized in the y direction with a very narrow angular spreading that comes. This one is mostly solitons that were emitted directly by the wave maker. This one are the ones that have been reflected at least once by the wall, and we see that they remain soliton only in that direction. It looks like the reflection on the side wall destroy actually the soliton, and they just change them into a dispersive wave. Okay, so to try to have more solitons, so we could try the sine. Well, we tried the sine, but it was not so efficient here. So actually what we did, because also we were used to do that for weak turbulence, is to use a random forcing. Okay, so we use a John-Swath spectrum, which is not so relevant here, but it was built in the software that drives the wave maker. And we use it as a random forcing. It has a specificity of having a very narrow peak at a given frequency that we can tune. So we have two different experiments here. So that's a low frequency forcing. So the period of the forcing is 5 seconds. That corresponds to shallow water, actually, 0.2, kh equals 0.2. And we clearly see the crests that are emitted from time to time, bouncing back from the wall on the left here. And this looks really like solitons. But now if we increase the frequency of the forcing, so 1 second, so now we are more going into the deep water regime. We don't see these crests anymore. It looks more like isotropic wave field with no really coherent structures like the one we see on the right. So if we compare the distribution of these two cases, so that the high frequency case, where we see that the distribution is not exactly Gaussian, but close to Gaussian, there is a slight skewness coming from nonlinearity. Actually, you can compute second order correction, this typhoon correction, and we see that they agree very well with this. So it's typically what we see in weak turbulence, actually. And when you go to low frequency, it's not surprising from the movie that we saw before, but we get this exponential tail of the PDF that is typical of the solitons. Okay, much with a skewness which is much stronger than the case above. And when we look at the spectra, they are very different, actually. Okay, so for the high frequency case, we have the blue spectrum here where the forcing is there. So we have a peak at the forcing, not so much thing going to low frequency and the power law decay of the frequency of the spectrum, which is typical of weak turbulence. So there is a cascade of energy, a direct cascade of energy. But if we force at lower frequency here, then this red spectrum has been shifted for clarity, but we recover this exponential spectrum that we saw before, with possibly a little bit of weak turbulence at high frequency where we are in the deep water regime. So again, we can do let me come back. So here, that's an effect of dispersion, okay, between these two experiments. The RMS, the root mean square elevation of the wave is almost the same, and we change the dispersion. Okay, now we can change also the nonlinearity. So in that case, we take a low frequency forcing, is 3 seconds, so it's still in the shallow water regime. But the difference between these two experiments is that now the root mean square elevation is much weaker here than there, so that the nonlinearity is much smaller there. And again, when we look at the Fourier spectrum, KXF, there is no soliton branch here, whereas there is a soliton branch on this side. And if you look at the cuts, indeed, here we have only the dispersive waves, whereas we have some solitons in that case. And so it means that if we come back to the phase diagram I showed you before for the 1D case, so if you remember, so the nonlinearity is here and the Ursel number is there. We saw that we had to add enough nonlinearity to get a soliton gas, but we had nothing here because in 1D we can't have weak turbulence. Okay. Now, if we go to the soliton gas, to the random forcing in 2D, we have a phase diagram that looks a little bit the same. Except that now on the bottom corner here, when the nonlinearity is too weak or the Ursel number is too small, because we go in the deep water regime, then we have weak turbulence here, and soliton gas in blue over there. Now, in the couple minutes that are left, I want to show you an experiment that was a kind of a game at first and is somewhat intriguing. So I told you that when we want to make a soliton, we recede slowly the piston and move it forward to generate the bump. But now we can do the reverse. We can move forward to the front and then recede fast. And what we get is what you can see here is a dispersive shock wave, actually, because we make a hole and then when the fluid goes back, you get this nice dispersive shock wave. So it's good looking. And now we could say, okay, well, we could do the same thing as with the soliton gas, right, to generate a gas of dispersive shock waves. And actually, what we did is we took the time series of the driving of the wave maker and just flipped the sign. Okay, so here that's what we get when we generate sine. So the dashed line is the motion of one of the wave makers. So it recedes slowly, then moves fast forward, and it generates this soliton in the middle of the tank. Here it's the reverse, so it goes slowly to the front and goes back fast to the back, and we get this rough and the dispersive shock wave here. And now, if you wait for a long time, you get to a stationary regime. And if you look at the statistical properties of these two cases, they are quite different actually. So the distribution of the soliton is the one I showed you before, and then the red curve is the one we get when we force the shocks, and it's still very close to the Gaussian distribution, so no solitons there. And when we look at the spectrum, there are the red spectrum that corresponds to the shock is both different from the soliton one. It doesn't have an exponential decay, but it's also different from the weak turbulence case we had before, because there is this huge plateau here, very large, so very flat actually. Well, there is a little bit of oscillation due to the modes of the box actually, and a very fast power law. So I don't have much more to say than just the observation, but it's actually quite intriguing. So I think it's worth thinking more about it. Okay, so in conclusion, so we could observe some kind of relatively dilute soliton gas in 1D and 2D with some specificity in 2D due to the finite size of the basin and to dissipation, which cannot really avoid. The consequence of this real life effects is a more complex phase diagram that we would expect just from the equations. And the nice thing is that we could observe both in that kind of experiment, both weak turbulence and soliton gas in different regions of the complex plane. So of course, we would love to have to generate more denser gas, and Stefan talked just before about how we could do that, try to do that. We would love also to have a better identification of solitons in 2D, but from what I've learned from the KP equation, there is an IST, but it's somewhat more complex than in 1D. So my knowledge, at least of it, is more than limited. It's almost non-existent. And I'm also very excited about this kind of coexistence of weak turbulence and soliton gas in the same experiment, most likely by changing slightly the parameters. And possibly you can have both of them at the same time in a single experiment, soliton and the energy cascade. And these shock experiments are also quite exciting, but I don't have much to say so far about it. So thank you for your attention.
Thank you, Nicolas. So we have time for maybe a couple of quick questions. Yes.
Yeah, so I like this movie very much. But one thing I'm seeing in the movie is that occasionally there's breaking waves. Is that happening?
Yes, well, that's clearly we sometimes we put a little too much energy in the experiment.
Just for our entertainment, I see.
Yeah, we were excited, so okay.
So that doesn't happen.
Let's crank up
But in the experiments that where you're recording data, you don't see so much wave breaking, or it's rather rare.
Well, the experiments where we can record the data, we don't have wave breaking. It's more like this way actually, because when we have wave breaking, the particles get holes inside, so we can't do this reconstruction.
Okay.
But we have data with the breaking with the local probe. Say.
Mm-hmm. Okay, thank you.
But yeah, but we for what I showed you, we avoid the experiments where wave breaking, and we have especially wave breaking along the walls because of the stems. Actually, this Mach wave that we see on the wall.
Yes, I have a question, Nicolas. When you measure the PDF for the dispersive shockwave gas, was there a reflection, or is just?
No, yeah, it's the full basin after like 10 minutes of forcing, continuous forcing. Then we get a stationary state, and then I get a PDF from the stationary state. Yeah.
Okay, thanks.
Just brief question: is it Kadamcev-Petriashvili equation with the sign when you can have also lump solution? Have you ever observed it?
No, the lump solution, you get them from capillary waves, actually.
Okay, so it's not your case. No.
In your coffee cup, but not here.
Right.
This would be much more tricky because dissipation would be very effective.
beautiful experiments. With regard to the last portion on shocks, you ran the experiment in a two-dimensional tank, but as I understood, you did not put in any angular dependence in the piston. Is that correct?
Yes, we did. There is like in that experiment I showed you, it was plus minus 15 degrees, which is not so much.
In the shock case?
Yeah.
Ah, okay.
So it's bouncing on all walls. Actually.
I see. But you could do that in your 1D tank.
Yes, but
as
we
well,
didn't
right?
think about it at that time.
Okay.
Actually, we thought about it thanks to Miguel Honorato, who was visiting us last winter when we were doing these experiments. He said, "Oh, we can do the reverse," and then we see this beautiful shock wave going through the tank. So we did not try yet in the 1D actually, but we could, yes, for sure.
Well, let's thank Nicolas again.
Yeah.